Hey everyone, welcome back to the channel. Today, I will be reviewing A Brief History of Time by Stephen Hawking. Let's get into this story. Okay, let me start out with the story, right? I used to read books a lot, but something changed in my brain, and now I can't even read normal words / letters, not even syllables, right? People have this perception that I like reading, probably because of this piece of plastic on my face that has these two lenses that extend my vision, that probably give me the appearance of someone who reads words, syllables, letters, perhaps even sentences. But I don't really read that much. I mean, I have a couple of book reviews on this channel, but I'm not really consistent with it, and I'm trying to get consistent with it. I'm trying to read as much as I possibly can, which is 3 words per day. For Christmas, I asked for books for Christmas. That's how smart I am, guys. That's how much of a mega, scratch everything, right? I read all the time. One of my cousins said, "Wait, Abraham, did you ask for books for Christmas? What is wrong with you, bro? Why don't you get some Air Force Ones?" I'm not much of a sneakerhead. I'm more of a reading head. Something I find helps me read is if I'm reading something I truly care about. I mean, I see a lot of romance books and things like that. I think that's what people are picking up these days. I was never really into romance as a genre, probably because I deal with so much romance in my normal life that I don't need to escape into World of War romance, you know? My life is like 50 Shades. I just talked way too much. Let me talk about the book. Out of the way, this is a pretty famous book, A Brief History of Time. Stephen Hawking, brilliant, renowned mathematician, not known for anything else. I mean, this guy kind of revolutionized the way we see physics and astronomy. Very smart guy. Died on Pi Day, March 14th. What a coincidence. A Brief History of Time. Here's what's in the book. This book has a couple of chapters. Acknowledgements. Forward to the 2016 edition. It's about our picture of the universe, space and time, the universe, uncertainty principle. It basically collects from super simple physics to things that Newton figured out not by being under an apple tree, but by being a genius. That guy was pretty smart. It goes pretty much from Newton and Galileo and Copernicus to Hawking. I mean, yeah, it actually is pretty interesting how, while uncovering the history of physics, Hawking ends up kind of inserting himself into the book because he is somewhat instrumental to the picture of the universe that we have today. I just want to say, pretty much anyone can pick up this book, read it, and get something out of it. Even if you only read the first couple of chapters, that is still way more than the general public knows, I guess. It was kind of easy reading at first because I've done chemistry and physics at a high school level, and I did like a semester of chemistry in uni. So a lot of these concepts make a lot of sense to me. Things like the uncertainty principle or the wave-particle duality of matter. And we get into way more complicated concepts. I say way more complicated, but to Hawking and his buddies, it's probably really simple. Things like light cones. something I can kind of visualize, I can kind of grasp what a light cone is supposed to represent. But as soon as light cones get used in a more complex context, I kind of lost it. Like, I'm still kind of struggling to understand string theory, probably because I have a stupid three-dimensional brain. Whatever. I mean, one of the greatest stories of all time is the story of 20th century physics, right? We start off barely knowing what an atom is, and I say we, I mean humanity, barely knowing what an atom is, and then going from that to, let's take this atom, put it in half. Actually, even Oppenheimer gets a shout out here because he was a pretty smart guy. Too bad he was a communist. Joking, I really have to watch Oppenheimer, I haven't seen it yet. I just didn't get enough time last year. Some of my notes, quarks, the 6 types, up, down, strange, charmed, bottom, top, the 3 colors, RGB. The concept of spin when it comes to particles is the fermions, the bosons, the gauge bosons, hadrons, all those things. Some of them have integer spins, like 0, which looks the same at all points of view. 1 looks the same every 360-degree rotation. Spin is kind of a semi-intuitive concept to wrap your head around. I like these accompanying illustrations every now and then. So these playing cards when it comes to electron spin or the double slit experiment, wonderful. What else do we have in terms of pictures? The bending of light. GV have been observed. Oh yes, gravitational waves have been observed. So on page 80, it says, and so difficult to detect that they have not yet been observed. I believe by now this is out of date because gravitational waves have been directly observed. Please prove me wrong, future Abraham, by showing me some math. It's very interesting stuff here. Imaginary time axis. Ooh, that's a very good one, a very good note. So it's just a way to, I believe, imagine space-time in a boundless finite form, or sorry, all of the universe in boundless finite form, which means that it could have been eternal. If you imagine we have 3 spatial dimensions and 1 time dimension, and the time dimension is moving in one way, pretty much. I mean, that's what the chapter of the arrow of time is about. But if you imagine non-Euclidean space-time geometry, I'm trying to remember this, and have an imaginary time axis in which you could go forwards or backwards, that ends up making a lot of other things make sense. Very interesting. I mean, Hawking pretty much catalogues very simple classical mechanics and the development of that to quantum mechanics, to general relativity, and having those 2 massively accurate models in their own domains break down when it comes to quantum gravity or singularities. If I may talk about one of my pet peeves when it comes to astronomy and cosmology, cause and effect is a direct consequence of the arrow of time. Something Stephen Hawking explains very eloquently. We have psychological arrows of time, there are thermodynamic arrows of time, and there's a cosmological arrow of time. Cosmological is the universe expanding, thermodynamic is entropy rising and energy being distributed freely throughout the universe, which I believe is a closed system, for all I can tell. And our psychological arrow of time, which is I remember yesterday, I don't remember tomorrow, because I haven't experienced tomorrow yet. And the way he accounts for the thermodynamic and psychological arrows of time being synchronized, well, not so much synchronized, but pointing in the same direction, is that the very act of having memory, and he uses the analogy of computer memory, in which energy is stored in a cell and some energy is lost as a byproduct, the very nature of forming a memory, which has a physical component and a thermodynamic component, cataloging a memory requires a rise in entropy, loss of energy in the form of heat or whatever biological and metabolic processes I have. So that means that in order to form memories, I have to, like, the memories have to be formed in the same direction as the thermodynamic arrow of time, and therefore I experience time in the same flow as entropy increases, and he therefore links the thermodynamic arrow of time to the cosmological arrow of time of the universe expanding. Just very interesting stuff. Our picture of the universe. So Stephen Hawking talks about models of the universe and how those have changed from Ptolemy's map of wherever to what we now know. Space and time, which we discovered, we thought they were like absolute, but they're not absolute. They're kind of wishy-washy. Space and time are interlinked, and when we find out that time can be bent, space is like, you know, space can be bent too, I guess, I think. Is that a consequence? I'm not a genius here. Or light cones, awesome. Elementary particles, very interesting to read about those, but that's kind of where Hawking lost me, because integer spin and particularly visualizing all interactions between particles as the result of other particles kind of warps my brain. Just thinking about how photons are waves and particles, and they're like exchanged and they push and they do things and they're emitted by things, and everything can be mediated by particles. It's very, it's just a little hard to understand. Here's where the book kind of gets off the rails. Black holes, which is Hawking's area of expertise, because this is what he and Roger Penrose were studying way back, and I believe that's what Hawking did for his PhD thesis. He posited the, Hawking radiation and black body radiation, I believe, because we now know that black holes can't last forever just because of losses of energy and increases of entropy. In 1967, however, the study of black holes was revolutionized by Werner Israel, a Canadian scientist who was born in Berlin, brought up in South Africa, and took his doctoral degree in Ireland. I don't know anything about this. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place then for a creator? Very interesting stuff. When you think about what general relativity predicts in terms of the origin of the universe, if the universe is expanding, at one point it was smaller, and then you go back and it was smaller and smaller and smaller. So it kind of logically follows that the universe came from a very small point, a singularity, infinitely dense, and at infinitely dense regions, gravity and quantum fields go wooey, and apparently all the four fundamental forces of nature are all unified as one. But a very crazy consequence is that time may have had a beginning, or if it didn't have a beginning, let's say time existed before the Big Bang singularity, then we would have no way of knowing what that time is, because at the singularity, at that point, with everything we know about science, at a singularity point, everything we know about everything else breaks down. We can't go further back than that, because our models of time just we can't crack it, right? So anything could have happened before the singularity, and it wouldn't have affected the current universe. So that's why Hawking says we just kind of chop it off and start at the singularity as the beginning of time. And when people say, okay, so what happened before the Big Bang? It is an illogical question. It's like asking Santa Claus, when you're at the North Pole with Santa Claus, like ask which direction is north, right? Every other line of longitude, others the longitudinal lines, they all point to the North Pole. So at the North Pole, which direction is north? Well, that doesn't really make sense, because that's where north begins. And I remember watching a YouTube short. Don't flame me, I watch YouTube shorts, alright? But Hawking was positing a possible geometry for time, non-Euclidean, so spherical geometry, in which it would have been like the Earth, kind of a closed, open geometry. And Hawking revisits this idea for a self-contained universe, but basically time could have been entirely self-contained on one, I guess, 4, 2, I don't know how many dimensional surfaces. It's mind-boggling stuff. It really is. Because when you get non-Euclidean geometry, so geometry that isn't flat but rather curved or hyperbolic, you can get really weird properties, like having a triangle with 3 90-degree angles in it. Wormholes and time travel. This one's interesting. With everything we know about time, with light being a speed limit for the universe, the speed of light in a vacuum, if you could hypothetically go faster than the speed of light, or c, you would be able to time travel into the past, just as a consequence of relativity. Really interesting. So probably time travel to the past is not allowed. That is the real reason why no one showed up to Stephen Hawking's time travel party. No other reason. Nothing at all. They just couldn't go there. If they could, they would. Let's talk about separating the art from the artist. That's definitely a good use of time. If I was reviewing a Michael Jackson album, or a Harvey Weinstein movie, or a Roman Polanski movie, or a Woody Allen movie, or a Kevin Spacey movie, Hollywood, man. But if I was reviewing any of those movies, I would also take care to mention that I don't admire these people as much. I'm just focusing on the art, the math, the equations, what makes sense. Because at some point, you have to acknowledge, right, J. Robert Oppenheimer, great example. His actions, his math, kinda ended up hurting a lot of people, and he was a communist. But his math was correct, so I'm gonna let it slide. This isn't a symmetrical video, I'm just realized that. But yes, separating the art from the artist, Stephen Hawking. Just by sheer virtue of existing as a theory of everything, string theory is kind of dumb. I watched this video by this physics YouTuber whose name escapes me, but her videos are really awesome. I really love them. I was listening to it and she made some good points about how string theory kind of ruins science communication. And I feel like the multiverse is the next thing to succumb to the exact same pitfalls that string theory did, which is string theory is non-falsifiable. We can't say whether this is or isn't the case. It's just there, right? And the fact is, string theory requires a lot of extra dimensions to work. But where are those hidden spatial dimensions? They could be folded up, Stephen Hawking says. They could be folded up, maybe they exist. But if they do exist, then we have Baroque symmetry, we have asymmetry, because at the Big Bang singularity, or slightly after that, just like how all the four fundamental forces unified into one force, all the dimensions of space and time should have been curled the same way, right? They should have had the same property of curviness. They should have had the same straightness, or whatever shape they had. So why is it that we have 3 dimensions that are this shape, and we have other spatial dimensions that are really curled up or really stretched out or whatever? Why? Why is there that asymmetry? Who knows? Any string theorists in the comments, feel free to put your theories that, again, we can't falsify because, oh, what's that? I don't have a detector for other dimensions? Oh wow, I guess no one does. Crazy, right? Crazy. Einstein's second great cause was Zionism. Can one thing in this book age well? Thus the possibility of time travel remains open, but I'm not going to bet on it. My opponent might have the unfair advantage of knowing the future. I like, I believe this diagram of a graviton in terms of string theory, very reminiscent of Feynman diagrams. I'm saying that, but I'm actually an idiot. Theories of everything. Alright, we have a bunch of theories to describe a lot of physical phenomena, and they make really good predictions in their own fields. They kind of break down when it gets to singularities, but whatever. And Stephen Hawking's solution is, alright, let's make sure that we can go forwards and backwards in time. Imaginary time dimension. So, just like how imaginary numerical dimensions, imaginary axes, that's the word I'm looking for. An imaginary axis allows for a freedom of movement and rotation when it comes to describing positions. An additional imaginary time axes, so I guess 2 time dimensions, something like that, may entitle quantum gravity to exist. It's kind of, I'm of the opinion that Godel might be right on this one. So Godel, I don't know what Godel's first name was, but Godel, he had this theory of this incompleteness theorem where he said no system of arithmetic is self-contained. Basically, if you have any algebra in any system, you can't really prove it. Kind of getting down to how all maths is fundamentally based off of axioms, like the axiom of choice, which are kind of arbitrary. Just like how in philosophy, if you go down epistemology deep enough, you get to logical presuppositions like causations, A is not equal to not A, things like that, things we take for granted, obviously because they work, things that can't ever be truly empirically proven, because to empirically prove something is to use those fundamental precepts. So anytime you use any maths, you can't really prove what you're saying. That's why it's so hard to prove 1 + 1 = 2. And by prove, I mean, it's only like, we're only 99% sure that 1 + 1 = 2. Man, this probably sounds really stupid, but it's true. I like another model of the universe, or of quantum mechanics, that I really appreciate is Richard Feynman's sum of histories, where every quantum particle goes through a wave of histories, goes through every possible configuration in a wave, right? And let me try and get this right. The collapsing of so that's what the superposition is, the particle doing every possible thing. But when you collapse the wave function, it takes adjacent waves and kind of smushes them together, I believe. And the waves that don't destructively interfere, those are the waves that end up making it. So those are the probable realities that actually happen. I'm an electron, I'm spinning around. You looking at me? You got me. I'm gonna collapse into the most probable configuration, which is me sitting like this. I love this book, man. Who would I recommend it to? People who like space, people who like science, people who like physics, sometimes people who like chemistry, but only really simple chemistry. If you like organic chemistry, get out of here. If you like zooming into an atom until you can feel the electron cloud surrounding you, read this book. You're gonna love it. Don't read this book if you don't like time, if you don't like space, if you don't like matter, if you don't like energy, if you don't like these things, you might not want to read this book. Again, it's kind of hard to digest, but when I say kind of, it's hard to digest. It's heady, it's cerebral. What else would you expect? One criticism I do have, and it's taking me really long to get to a criticism, not enough pictures, I need more pictures, and I would like more maths in this book. Nothing too complicated, maybe every now and then just showing equations, showing the evolution of math from F = ma to the eigenstates of the vector calculus, while I'm talking about the Minkowski space-time, and we curve it, and the Schwarzschild radius, and then we get to the Hawking radiation, and listen, if we pause it through enough tensors, the singularity, like, I'd like more math like that. especially considering Isaac Newton invented an entire branch of mathematics to describe motion, which you couldn't even do that accurately. What a dumb model. Alright, I could have done better. The three-body problem stumps you, Newton. Also, I like hearing about the pitfalls of scientists. I don't want to hear just what they get right, I want to hear what they get wrong. Isaac Newton thinking that there's an absolute space, an absolute frame of motion. Wrong. Einstein thinking, hey, maybe the universe didn't expand and it's been in a steady state, so let me add a cosmological constant for no reason. Wrong. Like, Einstein was wrong about a bunch of things. He was a very self-doubting person. Just couldn't trust the mathematics. But I wouldn't either, right? Imagine you come up with an equation and the equation just postulates something so out of this world that you're just, yeah, I think I did the maths wrong. Instead of thinking, yeah, everyone else's worldview needs to change immediately. I like that amount of humility. Like when Einstein doesn't become the president of Israel. The Catholic Church, on the other hand, seized the Big Bang model and in 1951 officially pronounced it to be in accordance with the Bible. Skip, 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 Nazi-occupied Austria.